Ramakrishna, Siddharth, whether I'm audible?
Yes, Ravi, you are audible.
Okay. So, how is the thing?
Yes, going on.
Okay. So, do you want to wait or can we start?
Yeah, well, have you done offshore projects, Ravi, before?
Option, yeah. What?
No, offshore.
Yeah, offshore also done and option also done. Yeah, tell me, what's actually your issue?
No, the calculate as per Windows as per API RP 2A WSD. So, do you have any?
Wind load.
Wind loads, yes.
So wind load, that calculation, it's okay. Wind load calculation and that one, it's comes from their input. It's not by mechanical. So
Okay.
So they give the what is the speed and what is the maximum the per hour
Yeah.
rate and that one, and they give some factors and that one. So this is the factor to be considered in our calculation and that one. So that
No,
factor and that speed we have to put in our PVLI to calculation and that we have to execute the.
No, but in PVLite API RP2A is not there, no? That code is not there.
Yeah, which is that is okay. So if that is not there, then you have to equivalent. You have to inform them. We are in PVLite it is not there. So we are going to calculate as per as or maybe the what is the civil code maybe applicable or frequently you will use. So you have to inform them. Yeah.
Our client is not so simple, man.
Okay.
He's very
Then you have to do the manual then wind calculation and that
manual
one.
only.
Yeah,
So,
man.
my question is, did you have any Excel sheet as per API RP?
API RP again, that API RP, the wind calculation, it comes from civil or structural person. It's not by mechanical. So you have to ask your civil or structural person, give me this is the factors and that one which is required in our calculation, these values. So just request them. They will provide you because for them it is a daily work. For us it is maybe sometimes we'll do in structure some work. So they will immediately give that these are the factors and these are the value and what they use to refer in structure design in that.
Yes.
So accordingly you can put. So normally our mechanical side we have to take care where the structures is coming, where your support is coming. So so that you have to take care and you have to minimize the weight of the equipment which due to this is an offshore platform and that one. So like that. Okay, Ramakrishna, you got your answer.
Yeah. Okay. Yes.
Okay, anybody, any other opinion about this? I think Abhishek and Atul, you joined late. So actually Ramakrishna is asking, is there any way to calculate the wind loads and that one as per API? Do you have?
No, as per API, I'm not aware of it. But yes, we normally use IS standard for wind speed.
No, but did you calculated the wind load and wind factors and wind speed by yourself?
No, I just have reviewed the reports, but not done.
Okay, once by yourself you're not done. It's maybe it's input comes from civil. Means in my case, we're done. It comes from civil or structure inputs. So we'll take that factors and we'll put in our calculation. That's we'll do.
Yeah.
I think Vishwanathan, you're coming first time.
Yes, this is my first time joining in this forum.
Okay. Can you please introduce to the group because we want to know better to you.
Yeah, basically I have introduced in the WhatsApp anyway.
Okay, you're material engineer, no? Right. Okay, thanks for joining. Because this Ramakrishna used to earlier, he used to many queries related to material. Ramakrishna, now Vishwanathan is in group, so you can start. Every week he has some material queries and that one, but we are in our group we are not anybody's material expert, so we missed to answer his queries and that. Ramakrishna, do you remember any of the queries?
Yeah, mainly HIC testing, NACE generally do not make it mandatory, but when it will be mandatory, that one question I have.
Okay, first let me answer this and after that you can ask other questions as well. So basically when it is in the SOAR environment, that is when the process fluid is containing H2S with water, okay, then we will go for this HIC testing, especially for plates. pipes,
Yes.
when you are seamless pipes only. When
Yes.
you are controlling the sulfur content to less than 0.01 weight%, then that becomes a resistant material. Then there is no means there is no tendency for cracking due to HIC. Okay, and for forgings and casting, when you restrict the sulfur content to 0.0258%, then they are inherently resistant to HIC. The most vulnerable product form is plate. Okay, because when there is a ingot, when you have an inclusion, when you roll the plate, the ingot into a plate, the inclusion will get elongated, and this elongated inclusion is the site for hydrogen getting trapped and then causing hydrogen induced cracking in sore environment. Okay, now the plates are plates. Even though you control the sulfur to 0.003 weight% as per NACE, you have to mandatorily do HIC testing because they are most vulnerable. Okay, so they have to mandatorily undergo HIC testing.
Is there
now,
any? Go ahead. I will ask.
Yeah, then when you do a welded pipe with plate, then again the welded pipe you need to undergo HIC testing. Okay, now seamless pipes are only excluded. Welded pipes, since they are made out of plate, you have to do HIC testing for welded pipes.
Welded pipes also. Okay. Now my question is, because I have seen some projects where even though it is south, it is HIC is not mandatory, and in some projects in the process data sheet they'll mention HIC is required. Like that, I see two requirements. That's right.
Okay.
So yeah.
When you are having a internal cladding with corrosion resistant alloy like stainless steel or 625 or those sort of thing, then the backing material, that is the backing carbon steel, will have to be NACE compliant, but HIC testing is not required. In some of the specifications, they specify like that. When you use a plain carbon steel or internally coated carbon steel plate or welded pipes, then that time the internal coating is not resistant. So basically, they will call for HIC testing. The HIC testing is waived for carbon steel in case of CRA cladded or like that. That is considered to be a barrier, and it reduces the tendency of HIC to the backing carbon steel.
No, because I see, it is not the case of CRA, it is a plain carbon steel, but still we didn't do the HIC testing because specification is not calling for in some projects. In some projects, they mandatorily put this note, so we have done. Is there any exemption for HIC in some case, depending on the level of severity of south? Is it?
Okay. For carbon steel, especially if you have declared that it is source service, for carbon steel plates, HIC test is mandatory. It is surprising for me to hear from you that some specification they have exempted, which is not not a correct practice. I am not sure. You can bring out the specification, and next time if you share it in the forum, probably we can discuss further on that. But in source service, if you declare that environment as a source environment, then HIC testing for plates and welded pipes is mandatory. Okay, it is most of the specification like Shell, ADNOC, Qatar, Saudi Aramco, most of the specification they will call for HIC testing of plates. There is no exemption to that.
Can I add something?
Yes.
Can I add? Yeah, actually, in some specification, there is two criteria. Source service is there, but in that specification, source service means sometimes moderate source and sometimes severe source. So in the severe source, HIC testing is mandatory, and where in the specification that is mentioned that moderate source service, in that case, HIC is not mandatory. In some specification, it is mentioned like that. So maybe that specific about that specification he is saying. I think.
Yeah. Vishnu, let me put my understanding also.
Yeah, please.
Okay. Yeah. So I read the spec NACE MR0175. It says if it is a repetitive kind of, if the client has executed a previous kind of job, similar kind of job, and he has an experience with that kind of conditions, then he may exempt something like that. I think it was there. I think in NACE, maybe based on that they are exempting maybe Yeah.
No, in NACE, actually these sort of NACE or any standard, they
Yeah.
don't always give, 1 or 0, the binary, yes or no, or, the
Yes.
the correct,
Yeah.
they always, they always give, means put it in such a fashion that it is always ambiguous.
Yeah.
I don't recollect any statement in NACE MR015 since I am using it day in and day out that, they are giving such a statement. A client specification may say that, not NACE, but a client specification may say that if
Yeah.
you are buying it from my reputed vendor, which vendor list, approved vendor list, probably this vendor is approved to supply plates with restricted sulfur content without HIC testing. A client specification may say that. NACE, I think it is not.
No. Okay. So, and in I mean, my next question is, when we'll go for a different kind of metallurgy. So, like, okay, stainless steel we know. Apart from that, maybe duplex or super duplex, or you see in some cases titanium we're going. So, where
Okay.
generally, especially in oil and gas industry, yeah, upstream,
Okay.
particularly upstream.
Okay.
Yeah.
You want to go for source service or something like that? You mean to
Yes.
say that,
Like
it isn't?
Yes.
Okay. Okay. So basically, this is governed by again NACE MR015 Part 3. Meanwhile, I will say so. So the selection criteria for CRA is governed by NACE Part 3, NACE MR015 Part 3. The parameters are temperature, partial pressure of H2S, chloride content, and pH. Okay. So it gives the restrictive limits on these 4 parameters. Okay. And then if the parameters, like if our operating conditions, chloride, pH2S, temperature, everything pH which falls within the limit of a particular material, the table is given in NACE MR0175 Part 3. If it falls below the value specified in NACE MR0175, then we choose that material. In most of the offshore application, the problem is we have a produced water, that is water coming along with the oil or
Correct.
gas.
Yeah.
It is having a high chloride content.
Yeah.
Okay.
Yeah.
So in this condition, as the temperature increases above 60 degrees C, then SS316 becomes not suitable.
Yes.
So basically, then we evaluate the other material, goes like this. Then we go for, after austenitic stainless steel, we go for, duplex stainless steel. Then we go for alloy 825. Then we go for the 6 moly material, UNS 31254. Then we go for also parallelly SDSS. Then we go for 625. So this is the order of things which we go. First is in CRA SS316L. Then it is evaluated for DSS, then it is evaluated for 825, then it is evaluated for 6 moly and SDSS, then it is evaluated for 625. Okay, so this is the only criteria which decides the material selection, that is temperature, pH2S, chloride and pH. Okay, so based on the operating parameters, we select the CRA.
Okay. Okay. Yeah, currently we are doing one applicability package. So in that, our equipments are duplex stainless, de-oiling unit, like that, IGF vessel, things like that. Yeah.
Okay, so the duplex in produced water treatment, what is the maximum operating temperature? Is it 80 or 100?
I think it is 80. Yeah, 80 degrees.
80.
85,
So
80,
basically,
yeah.
till 80 degrees C, they will specify DSS, and till 100 degrees C, they go for SDSS in produced water treatment circuit.
Okay. Thank you.
Ram-
So, and in case of like water based on chloride content, so how the material selection will be? I mean, if it's
Yeah, it is again based, see, if it is a pure water without H2S and anything, it is purely based on temperature and chloride.
yeah.
The main mechanisms are either pitting corrosion and crevice corrosion in terms of corrosion, and cracking is chloride stress corrosion cracking. So based on these 3 mechanisms, we evaluate the tendency of the process means the fluid, that is based on temperature and chloride content, the level of chloride, level of temperature. And we have the material, which is having, resistance to pitting and resistance to chloride SSC. Those charts are available. So based on that, we make the material selection.
Okay, so I mean, general practices. Maybe we can find from internet. Yeah. Yes.
Well, some charts are available like that. We can find it from Sandvik or the manufacturers like
Okay. Yeah.
Special Metals. They have some curves. The Sandvik they have given some curves. Avesta or Autocompu has they given their curves. So
Okay.
based on that you can choose. But be careful that those curves given for pitting tendency or pitting resistance, they use 6% ferric chloride solution. Okay, that is very aggressive solution, and that is a very low pH and highly corrosive solution. In that solution, they may have a temperature, for stating like SDSS for 45 or something like that, 40 to 45. Okay. But in reality, it can go higher, very higher based on our temperature and our chloride content. Okay, so that's where the role of corrosion engineer, materials engineer comes. That guy will come and use his experience and knowledge to select the material. Just I'm cautioning you that don't just go by the curve, because the environment what you are using as a saline water or water with chloride, and the environment where they have tested is both are different, and the testing is done in a very highly corrosive solution with 6% ferric chloride, so acidified ferric chloride. Okay, so if they say 35, it can go even up to 70. Okay, so the charts are relative resistance you can see, but you cannot exactly interpolate. You can approach a materials and corrosion engineer for selection.
Yeah. Thank you. Yeah, that's all for now. Yeah.
Okay, Ramesh. Okay, you got your own. Okay, Abhishek, you want to ask something?
Yeah. So first of all, I would like to thank Mr. Vishwanathan for giving his valuable insights about the HIC.
Yeah.
So my question is regarding this HIC only. Suppose we are designing an equipment of piping, as you mentioned, for source service, okay, where H2S content is there. So only HIC testing is mandatory, means only HIC is something which is applicable for source service, or any other factors also we have to take into consideration while designing any equipment which is having source service. This is my question to you.
Very good question, sir. Very good question. I thank you for that question, because the answer may help others also. So, okay. There are two criteria, sir. When you are having a carbon steel in sour environment, which is containing H2S and water, you have two type of damage mechanism. One is sulfide stress cracking, and one is hydrogen induced cracking. Okay. Now, for sulfide stress cracking, the material shall be NACE certified. Okay. If your material is NACE certified, then automatically it is resistant to sulfide stress cracking. Now the hydrogen induced cracking comes for the plates via testing, and for pipes, as I discussed, pipes and forgings, you via sulfur control. Okay. Now, in case of sulfur, the NACE material, what is the restriction? Basically, they will restrict the chemistry to 1% nickel, hardness to 22 HRC, and then sulfur content. They will say that it should not be a free machining steel. It should not having a higher sulfur content, and the sulfur content is also restricted. Okay. So, and then they have a lot of other restrictions, like, if you have a cold work, then you need to do a PWHT like that. And for weld, anyway, you need to control hardness, or otherwise you need to bring down the hardness to 250 HV by doing a PWHT. So there are a lot of restrictions given in part 2. But what I mean to say is, you need to understand two things. That is, in sour environment, we have two different mechanisms. One is sulfide stress cracking, and one is hydrogen induced cracking. So for hydrogen induced cracking, except plate sulfur control, for plates, it is HIC testing. For SSC, the material shall comply to NACE MR0. So it's a NACE certified material. It becomes a resistant to SSC.
So,
when you are at WPS, you have to qualify as NACE WPS PQR with hardness control.
Yeah. So, what type of condition? It is only SSC or it is HIC? How it is, or it occurs both simultaneously? How it is?
Okay. Now now we have to go a bit into the mechanism. If you are interested, I can go into the mechanism, or otherwise, can I share something?
Yes, sir. Yes, please.
I mean, if you have time, sir, because I should not consume more time, and it should not happen that you guys.
No, at least we learn one thing also,
mean,
it's okay,
having
but that to be better. So
Yes.
it's good. We'll means
Good.
in depth.
Sorry, sir?
If we
Yeah,
learn
all
something
are-
in the depth, it's better rather than just finishing. Okay, you can share. It's not issue. Everybody, I think nobody have
Yeah.
issue. Yeah.
Yeah. Just
Yeah,
let me
please
try.
share.
Give me 1 moment.
Okay, till then I think
1 second. Let me have.
Let me introduce myself. I am Abhay Mahajan. I am overall experience of 25 years in pressure vessel industry,
okay.
and currently working on ammonia storage tanks. And I am thankful to Siddharth that he has given me this opportunity to join here.
Thank you for joining our group also, because we want some experienced person in the group
Yes.
so that they can answer some of the queries which many juniors are there in the group also, so they can get some expertise, your knowledge on that one.
Yes, yes. Thank you, sir. Thank you. I'm thankful to that I have been introduced to this forum.
Yes.
Welcome, sir. Welcome.
Yeah.
And-
Welcome, sir.
Okay, Ajay Yadav, you want to introduce?
Hello.
Yeah.
Hi.
Hi.
This side Ajay, and I am having a 15-year experience in Ireland, and I am working as a package engineer.
Okay. Total, how many years experience?
15 years.
15 years. Okay. And you are not specifically on package, not on the static, right?
Basically, my background starts from the static, then package.
Okay, okay. Now you are handling package as well as static, right?
Yeah, both.
Okay, okay. Okay, I think Vishwanathan started sharing something. Okay, we'll continue. Okay, Vishwanathan.
Oh, yeah. Once ready, I'll notify you. Yeah.
Yeah, one more top-up question. What is the importance? How Amine service also? I want to know how it is different from Soul service.
No. What is the question, sir?
Amine service. Amine.
Amine, sir.
Okay. That's my favorite topic, sir. Okay.
Yes.
What do you want to know in Amine service, sir?
No, I mean how it is different from Soul, or it is related.
Oh, nice. Okay.
Yeah.
Okay. Okay. Amine, it's my very famous topic. Okay, the amine is used to basically remove the dissolved gases. Okay, CO2 and H2S from the gases.
Yeah.
Basically, you have acid gas which is having CO2 and H2S in high quantity, and then you want to make the gas sweet. So that's called gas sweetening unit. The gas sweetening is done with amine. Okay, and then they will use nowadays they are using tertiary amine. Earlier they were using monoethanol and diethanolamine and diglycolamine as well. And then nowadays they are using methyl diethanolamine, MDA, what we call. It is having a higher temperature. You can use that. Out of all the amine, the MDA is the highest temperature where you can use it. So nowadays they are going for the tertiary amine, and it has a better absorption as well. Okay, and then the higher limit, you can do without PWST, because the monoethanol amine and all, you have to mandatorily do the PWST because of the type of amine. It's susceptible to cracking. Okay, having said that, now there will be a contactor wherein the amine will come and counter currently it will flow with the gas, and then the amine will absorb the H2S and CO2, and then there is a rich amine. So, okay, now the rich amine having the acid gas loaded is anyway you have to design with source service.
Okay.
So from the downstream of the contactor there will be a flash drum, and then after the flash drum there will be a pumping, and then it will go to the lean rich amine exchanger, and then it will go to the regenerator. Okay. Now all the circuit up to the regenerator will be source service.
Okay.
Then the downstream of regenerator, the lean amine comes, and then it goes to the lean rich amine exchanger, and then goes to the filter, and then go back to the contactor. It is all non-NACE service, non-source service. Okay. The amine which is stripped of H2S will be non-source, and the amine which is rich amine, which is containing the acid gas loaded into it, is considered source.
Okay, Ramakrishna, you got?
Yeah.
Okay. Any other issue?
You carry on.
Yeah. Any other issue? Anybody want to? Okay. Just at the beginning, Abhishek, you want to ask something?
Yeah, so I want to ask this, when it is source service, so we have to make it a NACE compliant. So in the NACE compliant, we have to do you have to make sure that SSC and HIC testing is meeting the requirement. So we have to procure the material so that it complies to SSC and HIC requirement. So I think this is applicable only for carbon steel plates, carbon steel materials, not for SS materials. Is it so?
Yes, you are right. There is a beautiful theoretical background. Most of the people, even the experts, so-called experts, don't know why it is. There is a beautiful theoretical reason behind that. You know, the carbon steel is having a BCC. Okay, I think I have to find a lot of literature next time. Keep it ready to explain. Now I got my literature. Okay, the reason is different. The reason is this: actually, carbon is BCC, that is body centered. Okay, no, I'll share it on the group maybe. The carbon is BCC. Okay, the carbon is in the body centered cubic. Not carbon. The carbon steel is body centered cubic. Okay. Now you have atoms, and then it is BCC, body centered cubic. Yeah, it is body centered cubic. So in between the atoms, the gap in carbon steel, that is the BCC structure, is body centered cubic structure. In between the atoms, ion atoms, hydrogen is an interstitial atom. Hydrogen is an interstitial atom. Okay, first let me I have got the file. Let me explain the mechanism so that you understand from there, you know. So let me share it here. Am I sharing it, sir?
Yeah, it's coming.
Yes, come on. Yeah.
Yes, it's visible.
It was in the environmental. It was the same file, but it was the environmental assisted tracking. So, the weight H2S damage. Okay. So, okay. Now, this is what is basically we need to talk of. This basically, you have H2S corrosion. That is when the hydrogen sulfide is in water. First of all, we need to understand the difference between corrosion and cracking. Corrosion is nothing but your wall loss or thickness loss. Okay. The material corrodes, undergo wall loss, and then damage or cracking is nothing but you don't have a wall loss. So in other terms, what we call it as the corrosion is as a time dependent mechanism. That is, you can predict the failure time. In cracking, you cannot predict the failure time. So it is called time independent. Okay. Now H2S corrosion, I'm not going to touch much because it's very simple. You have H2S and you have water and it is going to corrode. Okay. Now in terms of H2S damage, that is nothing but there are many mechanisms. Like one is only we are telling about sulfide stress cracking. Then we have these are all H2S damage, hydrogen induced cracking, stress oriented hydrogen induced cracking. Okay. Then the stepwise cracking is a form of HIC. Is another form of HIC. Okay. And then there is a soft zone cracking. So all are H2S damage. Okay. So it depends upon your pH. It depends upon your where the cursor. You can see the cursor, my cursor? No, you don't see.
No, sir, but we can understand. No problem. Yes, we can understand. Yeah.
Okay. So now you have pH. Now have the heavy high H2S level, then hardness, PWHT temperature. All the steel making is nothing but sulfur content. Okay. High H2S means high tendency for sulfide stress cracking. Okay, high hardness means high tendency for sulfide stress cracking. If you do a PWHT, the tendency goes down. If there is a high temperature up to 149, okay, they say up to 149, but the SSC happens between 0 to 50. Okay, that's the most vulnerable temperature. Okay, and then steel making, you have higher sulfur content, you have a problem with sulfide stress cracking, and you have a pH. And the lower the pH, then the tendency increases. Lower means less than 4, less than like that. 4 is 3.53. I will tell you why the pH plays a role. Okay. Now we little bit understand the mechanism. The cracking of metal under the combined action of stress and corrosion in the presence of water and H2S. The corrosion is caused by water and H2S, and then the stress. Okay. And the material which is susceptible material, which is nothing but carbon steel. In this combination, material, any environmental assisted cracking will have 3 factors: material, and then stress, and then the corrosive environment. Okay, it's a circle. It's a 3 circle. Okay, now you have stress in the material. Okay, please note that I am using the word only for sulfide stress cracking. When it comes to HIC, it is not related to stress. Okay, when you have stress, when you have corrosive environment, and when you have a susceptible material, this form of cracking will happen. Okay. SSC is a form of hydrogen stress cracking. I will explain this in the next slide. the result is the absorption of atomic hydrogen that is produced by the sulfide corrosion process on the metal surface. PWC is beneficial in reducing the hardness and the residual stresses. Okay, now, okay, let me jump into the mechanism. Do I have it? Oh my god, I don't have the graph. Okay, the mechanism goes like this. First of all, H2S combines with water and then forms this Fe plus H2S gives iron sulfide. Okay, iron sulfide plus monoatomic hydrogen. Okay, now ideally speaking, in any corrosion reaction, this monoatomic hydrogen combines with another monoatomic hydrogen and forms hydrogen molecule, and then it will escape. Okay, now ideally speaking, H2 is a molecule and its size is too high that it will never go into the steel. It cannot penetrate into the steel. Okay. Okay. Now the problem is, I'm presenting this. Okay, I took it from internet. Now the problem is the monoatomic hydrogen generated will not form hydrogen. Okay.
Yeah.
They will not form hydrogen because of the H2S presence. The H2S is called a recombination poison. Okay, the H2S is called recombination poison. The H and H will not combine because of H2S presence. Now it is called recombination poison. Because of that, the hydrogen will go into the material. This is called cathodic charging. That is, the cathodic reaction is H plus E gives monoatomic hydrogen. The monoatomic hydrogen charges into the material. Because it cannot form H2, there is a concentration gradient in the solution in the wet H2S environment. It is having a high concentration of H plus, H monoatomic hydrogen, H ion, and then in the material which is having low hydrogen concentration, so automatically diffusion happens. Okay, and that's why I said in the carbon steel, the gap is 0.36 Armstrong. The atom, the interatomic distance. Okay.
Yeah.
And the hydrogen molecular atom is around 0.49 or something like that Armstrong. So now when hydrogen gets into the carbon steel, already the gap available for a person to sit is 0.36 Armstrong, but the hydrogen monoatomic hydrogen diameter is 0.49 Armstrong. So it will, once it goes into the material, it increases the tendency to crack. Okay, whereas in CRA, that is any austenitic stainless steel or anything, okay, where there is a austenitic phase present, FCC phase present, it is a FCC, phase centered cubic. The gap between the atoms is 0.52 Armstrong. Okay, 0.52 Armstrong. What is the hydrogen, monoatomic hydrogen, this one? 0.49.
Yes.
So it is completely soluble. So, no austenitic stainless steel, not only HIC, any form of hydrogen damage, austenitic stainless steel or any FCC phased material, material will never undergo. Okay. If it is a FCC material and if any damage they are telling due to hydrogen, just you can bluntly say it on the face that it will not happen.
Yes.
Okay.
So that's why carbon steel is more vulnerable, stainless steel is not vulnerable.
So
That's why no one will in the world will ask for. Yeah, please sir.
Yeah. So this is SSC, means this is sulfur stress cracking, right?
No, this is sulfide stress, not sulfide stress cracking. I'm talking about hydrogen induced cracking. HIC.
HIC. Okay. Yeah. Okay. Hydrogen is getting induced into the material. Okay. Yes.
Yeah. HIC. So basically, the hydrogen will not cause any damage to stainless steel, but it will cause damage to carbon steel and low alloy steel. Low alloy steel also BCC. Okay. So that one we should not forget. Okay. Now, this is the mechanism. Okay. The hydrogen gets charged into the steel, and then that's why it is causing problem. It is causing two type of problem. The cathodic charging is same. But it causes two type of problem. One is sulfide stress cracking. One is hydrogen induced cracking. For hydrogen induced cracking, you don't need stress.
Okay. Yeah.
Okay. That's why in HIC testing, if you see, you will not have any presence of stress.
Okay.
Okay. Whereas in case of SSC, you will apply stress basically. Okay, so I wanted to show the diagram. Okay, now I explained about the SSC. Now I explain about the HIC. Okay, planar cracking that occurs in carbon and low alloy steel when atomic hydrogen diffuses into. Now you understand the mechanism why it diffuses, how it diffuses.
Yes.
Okay,
Yes,
this H2S is the poison. H2S is the recombination poison. The H2S is the problematic thing, substance that makes it more, conducive to cracking and, the damage.
yes. Yeah.
Okay, that's why the source service we put this sort of restriction. If you remove the H2S, if it is a non-source service or if you remove H2S, then this problem is not there. Okay.
Yes, sir. Yes, sir.
So no externally applied stress is needed. Trap sites usually more in steel with high impurities. Okay, so where there is a impurity, what happens is this hydrogen will go and I think the cursor is coming. Good.
Yes.
Basically, if you see that there is a inclusion, then the hydrogen will come and stay here inside this. Suppose this is the thickness. Okay, you assume this as a thickness. The hydrogen from the fluid will come like this, and then in the impurity fully they will load here. They will not pass through this impurity. Fully in this inclusion, and the impurity means I'm meaning inclusion. Full inclusion, it will have fully surrounded with hydrogen. This is called pressure build-up theory. The hydrogen increases here and then builds a pressure. After some time, the hydrogen will combine here with another hydrogen and forms hydrogen molecule inside the matrix.
And further increasing the size.
And then no further increase. Once it forms molecule gone.
Okay. Yeah.
It will crack.
Yes. Intrinsically the size will increase, so it cannot increase, so it will create a stress. And
yeah. Okay. That is one theory. Second theory is that the too much of hydrogen itself will not combine and no need to form hydrogen. The too much of hydrogen inside the inclusion will itself allow cracking. Yeah. So there are many theories, okay, but then we'll just understand one or two theories and then we move on. Okay. Yes. Okay. So each theory is each PhD.
Yes.
Okay, blistering and HIC. So basically, now we talk about only HIC, strongly affected by inclusion and lamination. That's why we are restricting sulfur. Okay, sulfur is the main culprit which gets accumulated and then forms an inclusion. And when you roll, it becomes elongated inclusion in the plates. Okay. Now, if you restrict sulfur, then you are restricting the tendency of forming sulfide inclusion. Once you are restricting the sulfide inclusion, what will happen is that probably the hydrogen may come inside and then pass through also.
Okay. Yeah.
Okay, so that's the only intention of restricting the inclusion. That is sulfur content, so that it don't form inclusion, so that you don't get elongated inclusion. Dirty steels with a high level of inclusion or other internal discontinuities is not preferred. We don't want that. That's why they will have a high NDT requirement also. Like lamination should not be there for the plates. They should have a very good microstructure, etc. in source service. Improving steel cleanliness to minimize blistering and HIC damage. So that's the preventive measure. And then blistering and HIC damage develops without applied or residual stress. So the main difference between SSC and HIC is irrespective of PWST or not, it will happen because it is not dependent on residual stress. PWST does not prevent them from occurring. Whereas in SSC, reduces both hardness and residual stress, and SSC, it is stress dependent, so highly effective in preventing or eliminating SSC. Okay, that's why you have to have a NACE WPS with hardness control or with the WPS with PWST with controlling hardness for low alloy steel and all. So basically, that's the main reason. Okay. Now we have NACE MR0175 part 1, part 2, part 3. We just touched upon that. Okay. So basically, you will. Anyone knows this graph, or do I need to explain?
No.
Yes,
we are the static. We are not the material. So nobody.
Yes, sir. Yeah.
Yeah, but actually, it's means for static engineer also. Is it useful to understand this graph and all?
No, just a simple thing. I'll make it simple. It's it's a knowledge sharing forum. So I thought, if you want, I will tell. Otherwise, I can move around because I don't want that I occupy more time and others don't discuss the other issues. It should not happen that way. So
yeah, Abhishek, your answer. Yeah. I think your query is answered, no? Right? You have something.
Yeah, my queries are answered.
Yeah.